I forgot to mention this in the last video, but this is in our textbook chapter 10. Well, depending on which class of mine you're in. Sorry if the packet is mislabeled. It might be, it depends on your book. It might be in chapter 9, it might be in chapter 10. Because I teach the same thing in two different classes, but using different books. Anyways, you'll be able to find it. Especially if you look for keywords such as permutation and combination. In this video, I wanted to talk about what is the formula for mathematical permutations, what are the different notations that it can be used depending on the source, and when is it used to make sense. So let's look at example number 2 from our lecture notes. It says a FedEx driver must make 10 deliveries. In how many ways could he or she make those deliveries? This idea is called a mathematical permutation. So basically, you could use the permutation formula to solve this. Or, let's think about it more basically by the fundamental counting principle. Because if we're thinking about all of his deliveries, we're starting off with 10 packages in our FedEx truck. To begin with, there's 10 different places that we could start by delivering those. So it's kind of like, well, how many different things I need to do and how many choices do I have in each of those cases? So like the first choice, there's 10 different deliveries I could make. So when I'm delivering my first package, there's 10 options, so there's 10 outcomes. Then the next act in that chain would be, well, after I've delivered the first package, I have one less package in my truck. Now there's 9, again, with 9 different places I could deliver it. So the second delivery, there's 9 ways I could do that. Once that delivery has happened, that leaves me with 8 packages left in my truck. There would be 8 ways to deliver those packages. And if you can kind of catch my drift here, if we're delivering each thing, every time I deliver one package, it reduces the remaining amount by 1. But it's giving me a set of options, a set of outcomes, and it's multiplicative, each time multiplying by 1 less than the previous. So, after I've delivered the first 3, then there's 7 packages left, 7 ways to do that, then 6, then 5, then 4, then 3, then 2. And by the time there's only 1 package left in my truck, there's only 1 way I could deliver that, and that would give me my last outcome. Now all the packages would be delivered. There's been 10 steps to deliver those packages, and basically what it results in is a very large number of ways that I could have delivered those packages. And this is the key. This is the idea of a mathematical permutation, because it's like how many different arrangements. These are all key words you might notice with permutation questions: arrangement, order. Because in a permutation, the order in which something happens matters. Because if I change the order of those deliveries, it would be a different outcome in this sort of question. But basically, what this results in is the product of 10 times 9 times 8. Basically, by 10 and every consecutive integer multiplied all the way down to 1. And this is always what's referred to as a factorial. The shorthand for such a multiplicative chain is written in mathematical notation by an exclamation point. So it's not 10 with emphasis. It's this sort of exclamation point always has a very special meaning. Be careful if you're trying to do algebra with this, because algebra works a little strangely with factorials, which I wanted to discuss as well. But essentially, this stands for exactly this chain, 10 times 9 times 8. Of course, in a calculator, you could type in this chain, but what you'll see is that the factorial, if you can't, most calculators will have a factorial option. And if I start by typing in 10, if you go into math and then PRB in the TI-84 stands for probability, you can find formulas for permutations and combinations as well as factorials right in there. So the exclamation point is right there. And I could do 10 factorial, which ends up being a very, very great number of arrangements of those packages. In this case, it appears like we're going to have 3,628,800 different ways those deliveries can be made. And it's quite a staggering number, because what we have is a pattern of multiplication. If we have 10 different deliveries to make, there's a whole heck of a lot of different ways those could happen. A total, of 10 products. And the more and more you multiply, the larger and larger the outcomes become. And basically, we refer to this as a complete permutation. Using permutation notation, basically we have a permutation of n objects taken n at a time. And that's what these sort of functions stand for. In this case, we'd refer to this as P10, 10, because we have 10 objects and we're trying to permute them all, meaning we're trying to lay them all out, or basically fully deliver them all. And formulaically speaking, whenever the numbers match within a permutation, it's always going to be directly n factorial as the result. And we'll compare this to the better form of a permutation formula, which is if you're trying to, let's say we were to take the same example. Instead of delivering all 10 packages, we just wanted to deliver 5 of them, and notice how many ways we'd want to get that done. Basically, to deliver 5 of those packages, we would just cut off some of the chain, because if we have 10 packages and we're trying to deliver 5, where order matters, again, we would start with 10, then 9, then 8, times 7, times 6. And after 5 packages delivered, we'd be done. The remaining packages would be left in our truck, and it wouldn't affect the order of the outcome. And that's essentially what this formula down here does. But let's kind of phrase it in a new way. Let's look at example number 3, just to look at permutations a little bit further. So this is another very common type of question you'll see in these sort of chapters on permutations. It says a class has 30 students. They plan to elect 1 president, 1 vice president, and a treasurer. How many different ways can this happen? And another thing I like to mention is you can always look at these questions in a number of ways. You could look at them as using a permutation formula, or you can take the common sense approach, where here we have 30 different students in our class. You could label them as A, B, C, D, or whatever. We'd even run out because there's only 26 letters in the alphabet. But if we were thinking about actually performing these acts by using their number of outcomes, first we could think about who would be elected as president. Well, there's 30 students, so there's 30 ways to elect a president in that class. Then if we're thinking about how many ways could we elect a vice president? Well, it doesn't specify, but we generally assume that if they're the president, they're not also the vice president. That doesn't usually make sense. So we can kind of look at it in a similar example where each time an outcome happens, it's always going to be multiplied by 1 less. As we're electing a vice president, now there's only 29 students left in the class to choose from because 1 has been selected as president. And basically, this would leave us with 29 choices for vice presidents. And then when we come down to treasurer, well, now we've elected 2 already, so that leaves 28 for our last selection. And this would be the answer to how many outcomes could we have to this election? Again, just by using I say common sense approach, but it's by the fundamental counting principle. So basically, we'd have 30 times 29 times 28. Which would leave us with 24,360 different electorates. But again, this is often referred to as a permutation, and this is the formula for what we call a mathematical permutation. What I wanted to do is use this example to say, well, why does this formula make sense? So that you could kind of remember the logic behind this as if you ever encounter these formulas later. And these formulas are fairly common in if you ever take a course on probability or number theory or various other Calc 2. These sorts of formulas can come up from time to time. And I think they're worth knowing it's a good concept for a pre-calculus class. But anyways, if we apply the formula in this case, the way I like to phrase it is it's a permutation if the order matters. It's a combination if the order does not. And we'll talk more about combinations in the next video. This one's getting a little bit long. But here the order matters because if on my first selection, president versus vice president versus treasurer, it's different if I change the order of those acts, right? If I select the vice president's, the way I was going to phrase it would have made it a little bit more confusing, but we'll worry about combinations when we get there in a second. But basically how I'd write this is a permutation of 30 objects because it's sort of like, well, in my class there's 30 people. And then I was trying to select 3 specific people where each of those selections, it matters in which the way I select them. Because the vice president versus the president, it's different if I change the order of those. So the order does matter here. And if I look at this formula, well, it's a permutation of 30 objects selecting 3. So often people would say 30p3 or 30 permute 3. is kind of another way. Or another way that it's written in mathematical notation is often by a subscript 30 in front of the P for permutation, and then another subscript 3 after the P for how many are actually being chosen from that group. I like to think about it as how many are in the group first always should be larger or equal than how many things I'm actually selecting from the second. And then, basically those would all be equal to this formula that I have up above, which would be basically n is going to be the first number. 30 factorial would be in the numerator. And then in the denominator, it's always n minus r. The difference between these two things, n and r. 30 minus 3 is 27 factorial on the bottom. And that would be also equal to this as well. And basically, this formula, like, it's pretty horrible because it gives you, 30 factorial, that's going to literally be 30 times 29 times 28 times 27 times 26 times 20, blah, dot, 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 dot. A very, very long string of multiplication. But when you have a ratio of 2 factorials, there's generally a way to simplify or cancel so that it's not as bad. Like if we think about what 30 factorial would be, that would be 30 times 29 times 28 times 27 times 26 times dot, dot, dot. And then if we think about 27 factorial, that would be very, very similar. Instead of starting at 30, though obviously we would start at 27, it would be 27 times 26 times 25, dot, dot, dot as well. But basically, since those are all going to multiply all the way down to 1, we have a set of common factors in this factorial expression, where basically if you have one factorial divided by another, they will cancel each other out as well as canceling the factorials in a very specific way. Basically, you're going to take 30, multiply all the way down to one more in the denominator, and this would leave us with 30 times 29 times 28 would be all that's left of that fraction, which notice is exactly what we got when we did it via fundamental counting principle. And that's why I wanted to express what does this formula mean. Well, basically it's a way of counting the number of permutations of something. That's just a way of referencing how many ways can you arrange something. Another way you'll often see these sorts of questions is like say you have the letters A, B, C, D, E, F, G, and you wanted to know how many arrangements or like how many license plates can you make is another very common question of this sort. But basically arrangements or the ways in which they're organized or lined up or chosen often reference a permutation. And a lot of the time you can use a formula like this to solve those questions.